Let's consider the simplest element possible. This is a two-noded element that can carry tension and compression along its axis. The conventional name for such an element is a rod, or civil engineers call it a pin-ended truss. In some of the codes, such as the Nastran sequence, when they say rod, they also mean it can carry torsion. But I think you can figure out the generality of the element from the context. The theory that we'll do here will concentrate on the tension compression member. I'm going to do an overview of general two-noded elements, including these other forces and moments. Then we're going to really concentrate on the tension compression member in the derivation of the stiffness by equilibrium methods, and then by showing how we can assemble this body. So you can set several rods next to each other and join them. Then we will generalize the idea a bit and go back to some other simple line elements, such as an electrical resistor and pipe flow and so on. We'll end up doing some problems with our knowledge and show how we can assemble, how we can solve boundary value problems with the rod element. I'd like to start off by generalizing and looking at the most general case you could have for a two-noded element. Here we'd have a node A and a node B, and each of those nodes could have as many as 6 degrees of freedom, including 3 translations and 3 rotations. The idea of the element is that it's an elastic body connecting those two nodes, and it will transmit those forces from one node to the other. The basic relation we will want will be a stiffness. In other words, it will be the force at one node generated by displacements at the other node. And we've already mentioned the example of the rod. I've implied that there could be a torsional member involved. You can have the push-pull, and if you get into bending problems, you can have these beams and pipes and column action with only 2 nodes. And lastly, you can have elements that are nonlinear, such as a gap element, where a gap will close up and then the system becomes much stiffer. If we do specialize to the tension compression or the torsion element, then we have this situation. For instance, here is the pin-ended truss that we spoke of, and here would be an element that could handle torsion. And so you're looking at either a moment or a force that is collinear with the axis of the element. The Nastran series of codes have the rod element that combines those two properties. Now, what's not commonly appreciated is that the two-noded element can actually be a very dangerous element. If you do allow the full generality of all 6 forces and displacements at each node, then it is possible to cause a matrix relation that is non-physical, something like a perpetual motion machine. For instance, there are elements called ELAS1 and ELAS2 in the Nastran series of codes where the user is allowed to define that a horizontal displacement at node 1, say, can cause a vertical force at node 9. This would lead to a matrix which might be symmetric but is non-physical, in that you'll get an overturning moment caused by the compression of such an element. I know that this has happened because I've done it myself in studying a transfer press, and I was greatly puzzled by the fact that a line element like this, a so-called ELAS element that was being crunched between the jaws of the press, tended to throw the press off its foundation and on its side. And the reason being that I didn't carefully align the nodes so that the force relation was collinear with the axis of the element. There are companies that I've heard of, an aerospace company, which will take the data set for a given finite element run and then will scan it to make sure that any of these spring-like elements are properly formulated. So you can see at the outset here that there's some possibility to violate physical laws. And indeed, the real advantage of finite element methods is that normally we do build in conservation laws at the element level, and we normally do not allow such bad things to happen. So that by calling upon equilibrium, upon displacement compatibility, upon conservation of energy, normally our elements will be well behaved. But that general spring element remains the outlaw element in the library. Well, with that preamble, now we're ready to do some mathematics and actually calculate the properties of a simple rod element. And we'll concentrate on the simple tension compression element in which the forces are collinear with the element axis. We'll make this situation here where there's two nodes on the left and the right. We'll arbitrarily number those 1 and 2. There's a cross-sectional area of this element which will be considered to have constant properties, that is, materials and cross-sectional properties constant along its length. The axis of this element is straight, and the loads are going to be aligned with the axis, so our two forces are collinear. We will establish a coordinate system at the left end that will be what one would call an element coordinate system. It's at the same time what you might think of as a local coordinate system, and perhaps would be different than a global system describing a number of elements at the same time. Now, there really are 3 laws that we're going to invoke here, and we're a little bit short on theory at this point because we don't know the relevant energy law. However, for this simple element, because it's statically determinate, we can use equilibrium and get the full answer. Now, we will revisit this problem later on after we learn virtual work, and we'll redrive the stiffness matrix a different way. But for the time being, we're going to learn quite a bit, and not only about the element, but how to assemble. So I'd like to get some answers going here rather early in our study to give us some intuition. Now, the 3 laws that we might apply now, first of all, would be an equilibrium law, Newton's second law. Now, for statics, that would mean that a body here would have to be at rest and the forces would have to add up to be 0 along the axis. Secondly, we would consider the material to be linearly elastic, and so we'd have a uniaxial version of the Hooke's law. And then thirdly, we'll take infinitesimal displacement so that the engineering strain is the rate of change of the displacement field by the x-coordinate. Now, I find that mechanical engineers have the hardest time with this third item that I've mentioned. And indeed, it is a little tricky. I'm going to devote a slide to that, the next figure that we're going to see, and we'll talk more about that. But in conclusion here, with these 3 laws, we will be able to relate these forces and displacements at the right end with the forces and displacements at the left end, and essentially replace the continuum body here in the interior with a matrix of coefficients that will provide all of the stiffness information of that entire body. I've found over the years that many mechanical engineers have very good intuition for rigid body modes, but sometimes study it so hard that then when they come to straining motion, they don't quite get it. Now, for us, strain, especially this axial strain, does have some physical interpretation. It's the per unit stretching that's occurring along the axis. And the way you can find that is taking the position of an actual physical particle of metal before the deformation takes place compared with its location afterwards. Now, that difference is called a displacement. And the strain has to do with the way that that displacement is changing from point to point in the body, referred to the initial position or the unstressed body. This kind of infinitesimal elasticity is always referred to the undeformed body. If you ever have any worries about where you're measuring from, you always consider the undeformed body as a reference. Now, I show in this figure a body in blue that's the undeformed body, and then in red is a deformed body. I'm going to try to use red colors for things that are force-like and blue colors for things that are displacement-like in general. And so you'll notice that this displacement at the node at the left end is given in blue as the one in the right end. The interior field displacement I also have characterized with a blue arrow, and I'm using this script U as a measure of the field and the upright U as a measure of the nodal displacements. Now, those are intimately connected at the nodes. In other words, if you evaluate what the particle motion is through the script U, then as you evaluate that as you approach a node, you must recover in the limit the nodal displacement. Because after all, you're looking at particles and how they move from point to point in the interior. And as you approach a node, then you must recover the nodal displacement. So I've plotted that field displacement below, and it's a little bit non-physical in that I have to plot it vertically, which is not its real direction. So you have to, your mind has to go through a 90-degree rotation in a sense to comprehend that. Now the field displacement then would have varying values here along the domain of the problem from 0 to the length L of the element. And as I've mentioned, then this vector arrow has to eventually recover the nodal value as you reach the end. Now it's the slope of this curve that becomes our engineering strain epsilon x, which I call out here. And in general, that could change from point to point, but this element is called a constant strain element because when you deflect the right end and the left end, then the interior displacement field will be linear like this physically. And you can just imagine the proportional stretching that would go on over the body. But it's this strain then sometimes that is difficult for people. For us in this problem, it's a constant. One good thing that's been worked out in finite elements is a consistent sign convention. And with these two nodes in the problem, we're going to find that we use the same sign convention for both nodes, namely that it's a positive force and a positive displacement if it's to the right. So I show that in this drawing then, and I'll again mention that together these pair of displacement-like and force-like quantities always create work when you take the product. In a general case, it could be a moment and an angle, so it wouldn't always have to be a translation such as we have and then a force. Now let's bring into play our other physical law, namely equilibrium. And in this case, the summation of forces to the right should be 0. And that just means that the force F1 at the left end and the force F2 at the right end have to balance out. Now, of course, that means one will have to be negative and the other positive. We can arbitrarily solve for the second in terms of the first to show that sign sense. Now, the strain that we are using, the du dx, can be approximated in this case by the total length change from one end to the other divided by the total length of the original line element. And that just becomes a difference in the two nodal coordinates, u2 minus u1. Now, this is fortunate because now we have related the strain in the interior to the displacements at the ends of the element. So already we're doing a kind of a rough form of interpolation. Let's bring in another physical law, namely the one that Hooke originally proposed, was that forces are proportional to displacements. Now we'll use it in the stress-strain sense shown here, that stress is proportional through Young's modulus to strain. We previously, in the just derived equation, found that strain could be written as the difference of nodal displacements over the length. So now we have, in addition to an interpolation for strain, we now have an interpolation for stress in the body. Finally, we'll use the physical law for equilibrium again, using two free body diagrams at the left end and at the right end. Now you don't equate stresses, but rather you equate forces on such a free body diagram. The right one is a bit easier because of the sign convention. The sign convention in mechanics is that tension is positive as an internal stress, leading to the directions of the arrows for sigma x. That is a classical mechanics sign convention, not a finite element convention, and it's a little awkward. But nevertheless, on the right side, you'll find you must have the stress times the area, which is a force to the left, equal to the force F2. And I say that that's a more intuitive one because there's no sign reversal. But on the left end, the same thing holds algebraically true. In this case, it's the sum of the two forces must be 0, or conversely, that the force at the left end must be minus the stress times the area, and I show that here. You may need to stop and jot down some ideas here and make sure that you understand this, because we're really quite close to our first finite element stiffness matrix. So don't be afraid to pause and do some checking on the side. We've actually progressed a long ways now. We have the interior strain field and the interior stress field, both related to the nodal displacements. Then when we made the small free body diagrams at the nodes, we were able to relate that internal stress to the nodal forces. So it turns out we have enough information now. At the left end, the force had to be minus the stress times the area, and then we'll put in what we found for the stress here. At the right end, there was no sign conflict, and we found that the force at the right end also equaled the stress times the area. And if you look at these two equations, and if you start to think in matrix terms, which is a good idea, you'll notice that there are two unknowns on the left side. And if you view the displacements at the nodes as unknowns, then there are two of those on the right side, but they're linearly scrambled among these other physical parameters, A, E, and L. Better to rewrite those out in the form here and pull the variables out to the back like this, and then when you line your equations up, you begin to see that this is two equations in two unknowns, and you can furthermore group the terms on the right side into a small 2 by 2 matrix here times the unknown displacements. And so we now have a matrix law, and I think this is quite a noble goal of your work in this course, is to try to think in matrix terms rather than scalar equations. So here is our matrix law relating nodal forces to nodal displacements, and we have successfully removed the continuous nature of the body intermediate to the two nodes. In other words, all that remains are some lumped parameters, in other words, some constants that characterize the body entirely. So we can now call these a stiffness matrix K and summarize the results at the bottom. And this stiffness K is the first stiffness that you have encountered in our course. It's the first of many, and it really characterizes the geometry and the elasticity of this body. Let me rewrite that stiffness matrix to emphasize the symmetry in the problem. If I pull out the physical parameters EA over L, then I'm left with this matrix. This is a particularly nice form. The fact that you get the 1 and the -1 has to do with the static determinacy of the system, namely that the force on the one end is a negative of the other. There's another peculiarity, and that is that the determinant of this matrix is 0. Now, that's not an accident. That reflects the fact that this little element could slide along its own axis if it were free to do so. We call that a rigid body mode, and it's characterized by this fact that the determinant is 0. Notice that the elastic property is tied up in the Young's modulus E, and then the area and the length of the rod element are geometric properties. So the stiffness matrix captures the symmetry of the problem, the mechanical properties, that is the material properties, and the geometric situation. So it's quite a system interpretation of what would happen if you push and pull on the two nodes. Now, I want to make some comments here. The components in this matrix K are often given the subscripts I and J. Now, I stands for the row and J for the column. That's universal. And what we really have found now is not something that resists things as much as it conducts or promotes something. Now, what is it that it conducts? It conducts forces. So when you do this form of the equations that we're doing, we think of the stiffness terms as conductors of force from one node to another. And if we were doing an electrical system with the same philosophy, then what we have found are conductors. They're not resistors. And that might be a little difficult for many people, especially if you do experiments. And there's a natural reason for that. We'll talk about that in a minute. So what Kij is defined as is the force at degree of freedom I due to a unit displacement at only degree of freedom J. This is a wonderful theoretical idea, but it's rather hard to measure, because in order to measure stiffnesses, you would have to restrain all of the degrees of freedom in the problem to be 0 except 1. Then you would use a hydraulic jack or some other forcing mechanisms to move that 1 degree of freedom 1 unit. That would alter the forces on the others, and you'd have to readjust the other constraint mechanisms. So it's not that easy to actually measure stiffnesses. And as a result, I say here that experimentalists hate stiffness. Now, what is it that experimentalists like? Well, they like flexibilities, Cij. Now, the Cij is actually the inverse property, and it's defined as the displacement at a degree of freedom I due to a unit force at only degree of freedom J. Now, this is easy to measure because much as stepping on your bathroom scale and then watching the dial spin around, an experimentalist can apply a force at one point and then measure displacements at other points. In fact, at many points, and recover the flexibilities. And I did use that approach in my master's thesis some 35 years ago, where I was interested in vibrations of a delta wing, a small delta wing model, and that was quite easy to do. So the two concepts of stiffness and flexibility are important concepts and, in a sense, are mirror images of each other. Once we have a stiffness for a rod element available, then we can consider what would happen if we join several of them together. One of the first things that might bother a person is whether the coordinate system could be used in common for both of the elements, and that will turn out to be true, so the coordinates will not cause a problem. It turned out that the stiffness did not depend on the position of the element, but only on its length and cross-sectional area. So we'll be lucky in that regard. Now, I've seen assembly discussed by authors previously where a very mathematical approach is taken with a lot of summation signs, and frankly I never understood those discussions. I much prefer a topological argument where you show where each of the elements is embedded in a larger matrix that's of system size, and then you can immediately see how the stiffnesses connect the nodes, how they transmit forces from one degree of freedom to another. So we'll study assembly with two elements in question here. The one on the left I'll draw a little skinnier, and the one on the right a little fatter, so they appear to be different. And they indeed could have different lengths and so on. In a minute, I'll assign a stiffness coefficient to the one on the left, which we will call K1, and that's the EA over L coefficients, and then K2 we will call E2, A2 over L2. So we'll have a characterization of the geometry and material. How can we assemble? At the outset, you have 4 degrees of freedom in the exploded view. Yet, if we assemble by combining the 2nd and 3rd degrees of freedom at the pin joint here, then we only have 3 surviving system degrees of freedom. So, I think this is an important thing, that we're going to reduce our number of degrees of freedom, and so there's some collapsing of information onto a more reduced space. I will ultimately use different symbols for the assembly. I'll use capital symbols for the forces rather than the lowercase, so you'll be able to tell that at the end. And we'll carry a subscript E for the element displacements at the nodes, which will drop when we get to the assembly level down here. The approach will be to write out the matrices in the enlarged form for the system, which is a 3 by 3 matrix, rather than at the element level, which is 2 by 2. However, we do embed the element 2 by 2 matrix into the 3 by 3 space, so you can see where it overlaps. What I'm doing then is shown, for instance, in this left equation, where I've taken the equation for the left element with 2 force quantities here and 2 displacement quantities. I'm adding some trivial operations by adding what appears to be an unneeded 3rd coordinate here and multiplying by 0 in each case on the first 2 equations. Well, you can't stop me from doing that, because that adds nothing to the equation for the single element. Then the 3rd equation, which is trivial, is 0 equals 0, and pads out this form. So you should be convinced that this is okay, because we showed that was true for a single element. Likewise, for the right element, we embed it into the same system matrix, including the 2 forces that are on the right element in the exploded view. We show the stiffness matrix again, where, as I mentioned, we're using these coefficients in a lump form, calling them, in this case, K2. And we again have coordinates in the exploded view, except this one now becomes UE3. So we're almost there. What we really need to do to put these 2 equations in a standard form is to set UE3 equal to UE2. And that means we're going to basically join the center common nodes of those 2 elements. That is really the assembly right there when we set this to be true. And when you've done that, you then find that both the displacement vector in the left equation and in the right equation have the same form. Call it Z, just an abstract letter. And what we really have above then are 2 matrix equations which have a common Z vector on the right-hand side. Now you can use the laws of matrix distributivity, and we can add those quantities and handle them and manipulate them. First we do just a straightforward addition of the left side of the equations and the right side of the equations, which gives you this. And that's really just a vector addition. So that's completely legitimate. And then we'll combine those terms. We will factor out the P and Q matrices and combine them here with common outer parentheses. And then when you add matrices, whether they're square matrices or whether they're vectors, as on the left here, you can do what's called adding term by term. And by that I mean you'll add the little component x1 up here to the little component y1, and so I've summed those 2 vectors together under a common set of curly braces. Likewise with the matrix here. And you don't have to adjust the common displacement vector z because it's not been adjusted. Now, term by term means that you do exactly what we're showing here. And on the matrix, you have taken the stiffnesses from the separate elements and you have put them in the right positions and added them up. Neither of the stiffnesses contributed to this outside term here nor to this one here. So it's interesting that there are some zeros. In other words, there are some degrees of freedom which have no force connectivity. There's no path of force conduction directly between the first and then the far right degree of freedom. So we can add the forces likewise. We have the force at the left end, which now is an external force. The force at the right end is really an external force. We're not quite certain what it means to add these two forces that were external in the exploded view, but now in some sense are connected together. We know that the displacement at that point is a common displacement, and we could have given it the name either UE3 or UE2, and I've arbitrarily chosen UE2. So on the left we have some forces that are added, we have some stiffnesses that are added, and then we have the surviving degrees of freedom here. And it's the surviving degrees of freedom that are now the assembled coordinates for the system. And so that's pretty clear. This is pretty clear, but we need to think some more about what these forces are. What happens at that common interior node is so important that I'll break it out as a special small topic. And I like to call it a mental experiment. What I'd like you to think is that there's a pin that's been driven in through the two holes in the two adjacent rods, and that the pin holds the two elements together. So that's the physical mechanism. Then we'll do a free body diagram for that pin. I don't want you to remember this mental experiment too long, though, because when we get to problems that support moments at a joint, you no longer have a round pin that acts like a pivot. In fact, most finite element assemblies have nodes that act like welds, or be more like a square pin and a square hole, and it will carry a moment. But for the moment, think of just a simple pin at that joint. Then we'll do this free body diagram. I've already been given the sign convention for F3 and F2, so I can easily just say that by Newton's third law, every force has an equal and opposite reaction, that I can draw those with the sense shown. We won't make a special sign convention for the pin, but just use the general logic here. Then the force cap F here is a possible external force now, something new that we're going to add. And if you sum forces on that pin then, say positive to the right, you'll get this equation that the interior forces, the F2 and F3, have to add up to be this exterior force F. So I will use that fact and replace F2 and F3 in the middle position in the force vector as shown here. Now this really is dynamite. You may not know what has just happened because it's a little subtle, but we have eliminated the internal forces in this problem in favor of the external ones. In fact, the only remaining forces of any interest in the solution here are external forces. Now I can tell a small story that in analytical dynamics, that was one of their goals. If you've used Lagrange's equations or other energy-based equations, you realize that there was a lot of hooping and hollering to the effect that, aha, we don't have to find the forces of constraint. And that's exactly what happens here too. In the finite element method, in the approach that we're using, which is called the displacement method, we don't have to find the internal forces of constraint that help hold the elements together. We only worry about the externally applied forces. We've already said that we have only the surviving degrees of freedom remaining here on the right, and we know how to add up our stiffnesses here, that these stiffnesses connect the same degrees of freedom that they would have in the exploded view of the body, and primarily depend on the element connectivity and the way the elements are numbered and the nodes are numbered. And so we really should be able to do this assembly of the stiffness as well as interpret the forces and the displacements. Finally, let's rewrite our results for the system and use a specialized notation for the assembly. I'll use capital letters F for the forces and capital letters for the stiffnesses to remind us that these are assembled system values. And we'll still use a lowercase u for displacements, but we'll drop the subscript E, reminding us that it was an element exploded view originally. We have to have consistent numbering on these surviving degrees of freedom, so we'll renumber both the forces and the displacements from 1 to 3 rather than 1 to 4 as the original exploded view had. And then in symbol form, this will be our final equilibrium law. Now we found this entirely by equilibrium arguments as well as some geometric and material laws. If you do this process a couple times, and we'll do a little more in our problem session at the end of this lecture, you will develop intuition and suddenly it will dawn on you what this assembly process is, and you'll have it for life. I don't know if it takes a half an hour or 2 hours. It's something like that. I'm trying to remember when I first learned. And when it dawns on you how that topological embedding works, you'll be armored with iron plating. No one will ever be able to dent your armor after that because you'll understand it cold. And in fact, once you've done that and gotten that intuition, no one ever draws the exploded views again. And in fact, I'm sitting here in my consulting company, Automated Analysis, and out in the working rooms there are people doing assembled situations day in and day out where they envision the component or the structure and they put on the finite element mesh only in the assembled version. They never draw exploded views. Now there might be reasons to do sub-assemblies, but not for the finite element purpose of doing something with those internal forces, because once we've learned to assemble, we understand that we've suppressed the internal forces forever and we can deal only with the external cause and effect. I'm going to remind you again that the nodes are welds and not really the pin joint that we use temporarily on this simple element, so try not to remember that little mental experiment. Lastly, the rod element, which only supports tension and compression, is typical of what I call elasticity elements, 1, 2, and 3-dimensional elasticity, such as for solid bodies. There's another class of elements that I call structural elements, and these are the plates, beams, and shells, and they carry not only forces but also moments at the nodes. Now that we've finished our structural rod element, we can sit back for a moment and think about other comparable situations. In fact, there are some other simple elements now that we can directly write down. The one for torsion would turn out with, well, it would take 10 or 20 minutes work if we really derived it, but will turn out similarly. The torsional element also has static determinacy. It has a torsional stiffness that would be on the order of Gj over L. Again, you have a material and some geometric properties, and you get this symmetric form of the stiffness matrix. Angles are the relevant displacement quantity. Moments are the relevant force-like quantity. Then we'll go into a heat conduction element. If this were a small rod carrying heat from one node to the other, we would have this coefficient out in front. We would have the nice symmetric relation for the heat conduction matrix. The U in this case would stand for nodal temperatures and the F for nodal fluxes, and that would be the amount of heat per unit time, perhaps watts. So you might have degrees Celsius and then watts here. Electrical problems, you could do electrical resistor problems. now and connect them up in various patterns, it will turn out that the coefficient of interest would be, as I'd mentioned before, the conductance in the form we're doing it. And you'll find then that the resistor will conduct current from one node to another. Now here is the voltage at the node, and then here is the current that results. Another example of a simple element is the pipe carrying fluid. And this is actually kind of an interesting case. I have worked with such a problem in small classroom situations where we would solve 3 or 4 such elements coupled together. Here you have the pressure head at a node P that will cause a certain discharge Q. The conduction of fluid from one point in the piping network to the other will vary as 1 over some friction factor here. And if the flow were of molasses or some truly viscous fluid, then this would be a linear equation with constant coefficients. But more generally, if you look at diagrams like the Stanton diagram in hydraulics, you find that the friction effect here, or call it the conductance in the reciprocal form, will vary as the velocity. For instance, as a turbulent flow develops in a pipe, if you have a really rough pipe, the pressure drop might vary as the velocity, which is the discharge here, squared. So the true pipe problem lies somewhere between a linear and a quadratic relation here. It turns out that you can actually use that nonlinear effect in the equations, and you can iterate. You can guess an answer and improve it, and you will get convergence, luckily for conventional water pipe flow. So it's turned out to be a doable problem, and you can see that the simple element, at least in the linear case, is similar to our rod element. It's time for our first problem session. Now, the problems that I'm going to do are meant to illustrate some of the points that we've made. They're meant to extend you a little bit further, maybe, in some areas that I didn't have time to include in the lecture, and then to give you practice at some of the calculations. I'm going to start off with problem 1 that's going to be a full boundary value problem solution. So you see how a solution could go from start to finish with these little rod elements. I call this solution of a rod assembly. And what I've done is taken 2 line elements here, 2 rod elements, and pinned them together, and then pinned them at the left end to ground. I've put a live load of 1,000 newtons on the right end and no load in the interior. And the question is to find the displacements in the rod assembly. I could also have asked for the forces and the stresses and some other things. It is statically determinate, and you could see that 1,000 newtons will carry through the structure and react at the left end. But let's not assume that. Let's get that out as an part of the answer. In fact, you should be able to solve such a problem thoroughly by our stiffness ideas. This would be called a mixed boundary value problem, inasmuch as we have a displacement condition on the left end and a force condition on the right end. Now the intermediate node, number 2, because it has 0 force on it, that still is a force boundary condition. It's not a displacement boundary condition. And the interesting thing is that we should be able to tell from the statement of the problem either the force or the displacement at every degree of freedom in the problem. Some people find that surprising at first. It makes it a little different than a conventional classical boundary value problem, where many times you're only required to specify information around the boundary of the problem. Our problem here, though, requires that we say one or the other about the force-like quantity or the displacement-like quantity at every degree of freedom throughout the whole problem, on the boundary and the interior. So let's go into our solution now. Down below, I have taken the numerical values of these physical coefficients that we've been given for stiffness, and I've entered them and already have assembled the stiffness of the left element together with the stiffness of the right element. They overlap at the interior position, and you'll see that that is 3 times 10 to the 4th, which is just the sum of these two separate stiffnesses. Then on the degrees of freedom, we use the assembly degrees of freedom, U1, U2, U3. Of course, the one at the left has been constrained to 0, so that's our displacement boundary condition. Then on the right, we have the 1,000 Newton load, which is known, a force condition, and we know that there are 0 units of force in the interior. So I have left the unknowns in red here to show that we need to solve for those quantities. Now, it's always true that when you have displacement conditions in a problem, you've then already specified the field variable at that point. And this will, in effect, reduce the size of the problem because that can be exploited. Particularly when you set a displacement to be 0, that equation becomes relatively easy to separate out and solve as a separate final step. In our case, I'll do this slowly and show how that can happen. Once you see this, you'll understand how that works. The fact that there's a 0 in this first displacement position means that you have eliminated the first column of that matrix, because when you post-multiply by a matrix, each of those terms affects the matrix here column-wise. So I know that this 0 will knock out all of these terms in the first column. Knock them out, I mean cause them to be 0 when you multiply by 0. You could at that point deflate this equation and this set of equations by shrinking this to 3 rows times 2 columns and pulling out the 0 up there and making it a 2 vector, but thereby leaving a 3 vector on the right hand side. Now, matrix multiplication tends to sum over the nearby indices and will effectively eliminate the index that ranges from 1 to 2. Now, of course, that's the column index in the first matrix, and it's the row index in the second. Now we can do something further. We really have 3 equations and 2 unknowns. So we may take the first equation and set it aside. It has been the equation that is largely meant to describe U1, but that was set to be 0, and so we'll pull that equation aside, and it becomes merely F1 is a constant times U2. This could be solved later if needed, or can be ignored. Notice that F1 is a reaction in the system. So in other words, when you apply the live loads over here, you're able to set aside the equations for which you would find the reactions here, and those can be solved at the end if you wish. Many computer codes will ask the user, do you want to find the reactions? Sometimes they're called constraint forces in the problem. And if you don't ask for it, you won't get it, because it's a separate step. Now we're left with a 2x2 set of equations shown here, and this is a solvable set of equations. I know physically that we've removed the rigid body mode because we've pinned the left end, and therefore that pair of rods cannot translate along their own axis. They're constrained in space. Another way to look at that is to look at the determinant of this equation, and you'll find that it is positive. It's 6 minus 4